Welcome back to the Deep Dive. This session is built entirely for you as you prepare for one of the toughest challenges in medicine, the MD Anesthesiology Finals.
Absolutely. And we know you're aiming for that next level of understanding, especially for the Gujarat University syllabus.
That's right. This is where the deep physics meets, really the highest stakes of clinical practice.
Our mission today is very, very targeted. We are going straight into the engine room of the anesthesia machine.
The Flowmeters and the variable bypass vaporizers, or VBVs.
Exactly. Mastering these isn't just about passing an exam. It's because they are the absolute core of accurate gas and agent delivery.
And I imagine an examiner sees your grasp of these devices as a direct reflection of your commitment to patient safety.
100%. It's a proxy for your entire approach to the specialty.
Okay, so let's unpack that a bit. We constantly see flowmeters and vaporizers paired together in the theory exams. They often form the backbone of a big 20-mark long answer question. And they are, of course, absolutely central to the Viva. Why are they tested together so consistently?
Because they are a completely interdependent system. You can't understand one without the other. The flow meters control the gas flow into the vaporizer.
Right, they set the stage.
And the vaporizer then adds the volatile agent. So any mistake in the flow meter's output, any little inaccuracy...
is magnified down the line.
Precisely. Or if the vaporizer fails to compensate for, say, a drop in temperature, the final concentration delivered to the patient is wrong. They are the two most critical links in the delivery chain.
And when you look at past exam patterns, what's the fundamental principle that examiners are always probing for?
It's one word: safety. Always.
The safety.
Look at any past paper, DNB questions, university questions. They consistently demand that you can list and, more importantly, explain the safety features.
Specifically those designed to prevent what?
The delivery of a hypoxic gas mixture. That is the cardinal sin. The physics of a Thorpe tube, the biometallic strip in a VBV, they're important, but they're important because they explain how the machine keeps the patient safe.
That sets the scene perfectly. So let's dive right into that first core component: flow meters, principles, and construction. What's the fundamental definition we need to lock down for the exam?
Okay, at its heart, a flow meter is a calibrated device that does two things. One, it regulates the flow rate of a medical gas, your oxygen, your nitrous, your air.
Using the control valve at the bottom.
Yes. And two, it indicates that flow rate, usually with a visible float inside a glass tube. It's a simple, elegant application of fluid dynamics.
And on any modern machine, when we say flow meter, we're really talking about the Thorpe tube flow meter. Let's get into its construction. What is it that makes that design so special?
The Thorpe tube is all about its specific geometry. It's a glass tube mounted perfectly vertically, and it's tapered.
Wider at the top, narrower at the bottom.
Exactly. And inside, you have your float. The core principle, and this is a key phrase for your exam answer, is that the Thorpe tube acts as a variable orifice under constant pressure.
Okay, let's break that phrase down. Variable orifice. The opening changes size. What actually is the orifice here?
The orifice is the gap created by the float itself. When you open the valve at the bottom, gas flows in and pushes the float up.
Right.
The space between the widest part of the float and the inner wall of that papered tube, that's your orifice.
An annular orifice, a ring-shaped gap.
That's the one. And as you increase the float rises. And because the tube is tapered, that annular orifice gets bigger.
So that's the variable orifice part. What about constant pressure?
This is the clever bit. The float is just suspended there in the gas stream. The forces are balanced. You have gravity pulling it down.
And the pressure of the gas pushing it up.
Right. It's the pressure drop across that orifice that supports the float's weight. So for any given stable flow, the float will find a position where those forces are in equilibrium. That position, that height, directly corresponds to a specific flow rate.
Which is why the tube has markings on it in liters per minute.
Exactly.
Yeah.
The calibration is printed right on the glass.
This design, then, seems to demand gas-specific calibration. You can't just have one tube for all gases. Why not? Why can't I use an oxygen flow meter for nitrous oxide?
Because the entire system, the entire balance of forces we just talked about, depends on the physical properties of the gas itself. And we have to be concerned with two main properties here: viscosity and density.
Viscosity and density.
Every single Thorpe tube is manufactured for one gas and one gas only. The precise taper of the glass is calculated for the flow characteristics of, say, oxygen.
So if you were to run nitrous oxide through that oxygen-calibrated tube?
The reading would be wrong, completely inaccurate. Because nitrous has different viscosity and density, the pressure drop needed to hold the float at a certain height is different.
So for the same actual flow of gas, the float would sit at a totally different level.
Absolutely, which is why they are color-coded and physically separated on the machine. It underlines how the physical construction is absolutely central to its accuracy.
And what about the float itself? Does its shape matter?
Oh, very much so. The float's behavior is part of the calibration. You see different types. There's the simple bobbin, which is a bit like a spinning top.
And you read that at the very top edge.
Correct. Then you have what's called a skirted or a plummet float. These are often designed to spin, which helps keep them centered in the tube and prevents sticking.
Where do you read that one?
You read that at the shoulder, the widest part. The shape is designed to be stable and less affected by things like static, ensuring the reading is repeatable, and repeatability is everything in calibration.
Okay, that makes sense. Let's build on that and move to flow characteristics in calibration. This is where we have to really get into the physics of how gases move. So, laminar versus turbulent flow.
This is the absolute bedrock, and we use a value called the Reynolds number, or Re, to define which state the flow is in.
Right. So let's start with laminar flow.
Laminar flow is smooth, it's streamlined. You can imagine the gas moving in neat parallel layers that don't mix.
Like cars staying perfectly in their lanes on a highway?
Great analogy. This happens when the Reynolds number is low. The range you need to remember is between 0 and 2000.
And what's happening mechanically in that state?
Under laminar conditions, in a straight tube, the velocity profile is parabolic.
Parabolic.
Think of a bullet shape. The gas is moving fastest right in the center of the tube, and the velocity drops off until it's actually 0 right at the tube wall because of friction.
And what physical property governs that kind of flow?
In the laminar regime, it is all about viscosity. It's described by Poiseuille's law.
Okay. Now, let's contrast that with the other extreme, turbulent flow.
Turbulent flow is the complete opposite. It's chaotic. You have random eddies, swirling currents, lots of mixing. It always happens when the Reynolds number gets high, specifically greater than 4,000.
And that region between 2,000 and 4,000?
That's the transitional zone. It's unstable. A tiny disturbance can flip the flow from laminar to turbulent.
And in fully turbulent flow, what's the dominant physical property? Is it still viscosity?
No, and this is the critical distinction. In turbulent flow, the pressure drop is primarily governed by the gas's density, not its viscosity.
Viscosity for laminar, density for turbulent. That distinction must be crucial for how the Thorpe tube actually works.
It's everything. It explains the low flow versus high flow behavior. The tapered shape of the tube is specifically designed to handle this shift.
How so?
Think about it. At low flow rates, the float is near the bottom of the tube.
Where it's narrow.
Right, so that annular orifice is very small and constricted. The gas flow through that narrow gap is mostly laminar.
So at the bottom of the scale, the reading depends on the gas's viscosity.
Exactly. The calibration at the low flow end is viscosity dependent.
And as the flow increases and the float rises,
It moves to the wider part of the tube, the orifice gets much bigger, the gas velocity increases, and the flow becomes increasingly turbulent.
So at the top of the scale, the reading is dependent on the gas's density.
That's it. This is why the taper of the tube isn't uniform. It's a complex curve designed to account for this shift from viscosity dependence to density dependence as the float rises. Nailing that point in Viva shows a real depth of understanding.
That's a fantastic detail. Before we leave this, let's just touch on the importance of correct reading position again. Why is being so precise about reading the top or the shoulder of the float so vital?
Because that's where the manufacturer calibrated it. If you're using a bobbin and you read the middle instead of the top, you are introducing a systematic error into every single measurement you make.
It seems small, but I guess it adds up.
It really does, especially in low-flow anesthesia, where your total fresh gas flow might only be 1 liter per minute. A reading error of just 100 mils is a 10% error in your total flow. It can absolutely affect your delivered agent concentration.
That kind of attention to detail really defines an expert clinician. Okay, let's shift gears now to what you said is the highest yield topic, Flowmeter safety features. We need to be able to list and explain these cold.
Absolutely. There are multiple layers of safety, starting with the most obvious, visual and physical identification.
You mean color coding?
Exactly. The cylinders, the pipelines, the pressure gauges, and the Flowmeter blocks themselves are all colored according to a standard. Oxygen is white internationally,
Green in the U.S.
and nitrous oxide is blue everywhere. It's an immediate visual check to prevent you from connecting the wrong gas supply or adjusting the wrong knob.
But there are more than just visual cues. There are safeguards you can feel.
Yes. The tactile and shape differences of the oxygen knob are a mandatory safety feature.
How is it different?
The oxygen control knob is always unique. It's typically larger, it has a fluted or knurled edge that you can grip easily, and it often sticks out further than the other knobs.
So you could find it and turn it on with your eyes closed.
That's the entire point. In an emergency, in low light, under immense pressure, you can identify and operate the oxygen flow purely by touch. It minimizes the risk of accidentally turning down the oxygen when you meant to adjust the air.
A true lifesaver. But the most critical safety feature, the one that's built into the very plumbing of the machine, is the sequence of flowmeters. Why does oxygen have to be the last one in the chain?
This is a non-negotiable design rule. Oxygen must be the downstream flowmeter. It has to be the last gas to enter the common gas manifold before it heads to the vaporizer.
And the reason for that is to protect against a very specific type of leak.
Yes. It's designed to protect the patient if there's a leak or a crack in one of the other flowmeter tubes, say the nitrous tube.
Okay, walk me through that scenario. What happens if oxygen is upstream?
All right, imagine the flow is oxygen first, then nitrous, and there's a crack in the glass of the nitrous flowmeter tube. The gas mixture is now leaking out through that crack before it ever reaches the patient.
And you're losing both oxygen and nitrous.
You're losing the final mixture. The proportion you think you're delivering is not what's leaving the machine.
Now let's reverse it. Put oxygen as the last downstream flowmeter. What happens now with that same crack in the nitrous tube?
The nitrous leaks, yes, but the oxygen enters the manifold after the point of the leak. So while the total flow might be lower than you set and the nitrous concentration is off, you are guaranteeing that all the oxygen you're delivering is going into the final common gas outlet.
It maximizes the FiO2 in whatever gas mixture is left.
It's a mechanical failsafe. It's designed so that in the event of a downstream leak, the final gas mixture will become enriched with oxygen, not depleted. It's a beautiful piece of safety engineering.
And that's often part of a larger system, right? The proportioning systems.
Yes, the failsafe systems or minimum oxygen flow ratio devices. These are often mechanical or pneumatic links between the oxygen and nitrous oxide valves. They ensure that if your oxygen pressure falls, the nitrous oxide flow is automatically cut off or reduced. The whole ecosystem is designed around that one goal.
Preventing the hypoxic mixture.
Always.
Perfect. Let's pivot now to the scary part. Flowmeter errors and artifacts. You flagged this as very high yield for the Viva. These are the ways the flowmeter can lie to you.
They absolutely can. And a common one to start with is the back pressure effect.
Back pressure from where?
From everything downstream of the flowmeters. The vaporizer, the breathing circuit, a stuck APL valve, positive pressure ventilation, PP. All of these create resistance to flow.
And that resistance creates pressure that pushes back up into the flowmeter block.
Exactly. Now, flowmeters are calibrated at normal atmospheric pressure. When you introduce back pressure, it slightly compresses the gas inside the Thorpe tube. It increases its density.
Okay, so the gas is denser. How does that affect the float?
That denser gas exerts more force on the float for a given flow rate, so it pushes the float higher than it should be.
So back pressure makes the flowmeter overread.
Correct. The indicator says you're delivering 5 liters per minute, but the actual flow leaving the common gas outlet is less than that. The patient is getting less gas than you think.
That's incredibly counterintuitive. More resistance makes the reading go up. What about straightforward physical failures, like leaks and cracks?
Leaks are insidious. A tiny crack in the glass tube or a loose fitting at the top or bottom means gas is escaping. If the leak is before the float might read low. But the real danger is a leak in the common manifold after the gases have mixed.
Because then your final calculated gas mixture is compromised.
Yes, and this is why the daily machine checkout, the pressure leak test, is not just a box-ticking exercise, it's a critical safety check.
What about when the machine gets bumped or isn't level? The tilting or sticking of the flight.
Tilting is a big problem. The whole system relies on gravity acting perfectly vertically along the axis of the tube. If the tube is tilted, gravity isn't pulling straight down on the float anymore.
So the balance of forces is upset.
Right. And the float will read inaccurately, almost always reading higher than the actual flow. Sticking is another issue, often caused by static electricity or just dirt in the tube. The float gets jammed and then suddenly jumps or falls, giving you a completely unreliable reading.
Okay, we touched on this before, but let's really detail the physics of the effective altitude. How does lower ambient pressure mess with the flow meter?
Right, so at high altitude, the ambient pressure is lower. This means the gas inside the tube is less dense, it's thinner.
And we know the high flow end of the scale is density dependent.
Exactly. When the float is high up in the tube, that less dense gas is less effective at lifting it. The pressure drop across the orifice just doesn't provide as much lift.
So the float doesn't rise as high as it should.
Correct. The flowmeter will underread. It will tell you the flow is lower than the true volumetric flow that's actually passing through it.
So at altitude, you might think you're delivering 5 lemon of oxygen, but you're actually delivering more.
Potentially, yes. The reading is inaccurate compared to its sea level calibration. This leads directly to the consequences of incorrect gas delivery.
The ultimate consequence being the hypoxic mixture.
That's always the worst-case scenario. If the oxygen flow is reading falsely high due to back pressure, or the nitrous is reading falsely low due to altitude, your delivered FiO2 could be dangerously low.
So as the clinician, how do you detect these errors clinically? What's your safety net?
Your number one independent, non-negotiable safeguard is the oxygen analyzer.
Which is in the breathing circuit itself.
Yes. It is measuring the actual concentration of oxygen being delivered to the patient, completely independent of what the flow meters are set to. If your flow meters are set to deliver 50% oxygen, but your analyzer is reading 21%,
You have a massive problem.
you have a critical failure. It could be a leak, a broken flow meter, a pipeline crossover, but you know instantly that what the machine is telling you is wrong. You believe the analyzer.
That concludes a really deep look at the gas flow path. Let's now move on to the next stage, adding the volatile agents. Time for an introduction to vaporizers.
The vaporizer. This is the device that takes a liquid anesthetic agent, turns it into a vapor, and then adds it to that fresh gas flow in a very, very precise concentration.
We're moving from fluid dynamics to thermodynamics now.
We are. It's a whole different set of physical principles.
So how do we generally classify vaporizers?
You can classify them in a few ways. By how they regulate the concentration, by their temperature compensation, or by where they sit in the circuit. But for exams, the most useful classification is probably plenum, or variable bypass vaporizers, which sit outside the breathing circuit.
And these VBVs have really become the workhorse for our standard agents like isoflurane, sevoflurane, halothane. Why is that?
The VBV design is just brilliantly robust and reliable. It's a mechanical system that is self-compensating for a lot of environmental changes, which makes it incredibly safe without needing a lot of complex electronics.
Elegant.
It is. It works on a simple principle of splitting the gas flow as long as the agent you're using has manageable physical properties.
What do you mean by manageable?
Meaning it doesn't vaporize so easily that it becomes uncontrollable, and it doesn't require a massive amount of gas flow to dilute it down to a clinical concentration.
That makes sense. Let's get into the mechanics then. Variable bypass vaporizers construction. Walk us through the key components.
Okay. So fresh gas from the flow meters enters the vaporizer. The first thing it hits is the splitting ratio valve.
And that's controlled by the concentration dial on the top.
Precisely. That valve does exactly what its name suggests. It splits the incoming fresh gas flow into two separate streams.
And where do those two streams go?
The larger stream, usually most of the gas, goes through the bypass chamber. It completely avoids contact with the liquid anesthetic.
The clean stream.
Right. The other, much smaller stream is directed down into the vaporizing chamber, and that's where the liquid agent is held.
What's inside the vaporizing chamber to help the process along?
This is the clever part. The chamber is filled with wicks.
Wicks. Like in a candle?
Sort of. They're strips of absorbent material that are soaked in the liquid anesthetic. They draw the liquid up via capillary action, which massively increases the surface area for vaporization.
So you get much more efficient vaporization than you would from just the surface of the liquid pool.
Orders of magnitude more. The whole point is to ensure that the small stream of gas that passes through this chamber becomes fully 100% saturated with anesthetic vapor.
Okay, so you have one stream of clean gas and one stream of highly saturated gas. How do you get to, say, 2% isoflurane?
The two streams then rejoin at the vaporizer outlet and mix together. The control dial, by setting that splitting ratio, determines exactly how much saturated vapor is mixed with how much bypass gas to produce the final concentration that you dialed in.
And this is why they have to be agent-specific.
Absolutely non-negotiable. The splitting ratio is calibrated for the specific saturated vapor pressure, or SVP, of one agent. If you put isoflurane in a sevoflurane vaporizer, the output will be dangerously incorrect because their SVPs are completely different.
Let's talk about the biggest challenge in the working principle of variable bypass vaporizers, and that's managing the effect of temperature and vapor pressure.
This is the absolute key to their function. Vaporization is an endothermic process.
It uses up heat.
Yes, it requires energy, the latent heat of vaporization. As the liquid agent turns into a gas, it sucks heat out of the remaining liquid and the metal casing of the vaporizer.
So the vaporizer gets cold.
It gets very cold, especially during high flows and high concentration settings. And if you don't control that cooling, the liquid's saturated vapor pressure will drop.
And if the SVP drops?
The gas leaving the vaporizing chamber will be carrying less anesthetic vapor, and your final output concentration will fall, maybe to a point where the patient is no longer adequately anesthetized.
So the VBV has to fight against this cooling effect constantly. Which brings us neatly to compensation mechanisms. You said this is an exam favorite. Let's break down the three main types.
We have to start with temperature compensation because that's the most immediate threat. Modern VBVs use a clever mechanical device to do this. Usually it's a bimetallic strip.
Okay, what is a bimetallic strip and how does it work here?
It's simple, really. It's two different metals bonded together, and these metals have different coefficients of thermal expansion.
Meaning they expand and contract by different amounts when the temperature changes.
Exactly. So as the vaporizer cools down, this strip bends in a predictable way, and that bending motion is physically linked to the flow-splitting valve.
So it's just the flow based on temperature.
Yes. As the temperature drops, the bimetallic strip moves and automatically allows more of the fresh gas flow to enter the vaporizing chamber and less to go through the bypass chamber.
Wait, that seems backwards. If the vapor is less concentrated because it's cold, why would you send more gas through there?
It's about maintaining the final output. Think of it this way. If each unit of gas coming out of the vaporizing chamber is carrying less drug because it's cold, you need to mix more of those less potent units with the bypass gas to achieve the same final percentage.
Ah, I see. It's dynamically adjusting the mixing ratio to compensate for the falling SVP.
That's it, exactly. It's beautiful, passive, mechanical feedback.
That's brilliant. What about flow compensation? Does the output change if I use a really low fresh gas flow versus a high one?
It shouldn't, within limits. Modern VBVs are designed to be flow-over and are compensated to provide a pretty constant output across a wide range of clinical flows, say from 0.5 up to about 15 liters per minute.
How do they achieve that?
It's mostly down to careful engineering of the internal resistances of the bypass and vaporizing chambers. They're designed so that the splitting ratio doesn't change disproportionately when the total flow changes.
Okay. And now the third, and maybe the most crucial one for the Viva, pressure compensation. How does a VBV handle changes in ambient pressure, like going up to a high altitude?
This is a key advantage of the VBV design. It automatically compensates for changes in ambient pressure.
Automatically. How?
Because of the way it works. The VBV is designed to output a certain volume percentage of vapor. Now, what really matters for anesthesia is the partial pressure of the agent reaching the brain.
Right, based on Dalton's law.
Yes. When you go to a higher altitude, the total ambient pressure is lower. The VBV still puts out, say, 2% Idoflurane. But because the total pressure is lower, the partial pressure of that 2% would also be lower.
Which would mean less anesthetic effect.
The VBV's internal mechanics, because of how the pressures and flows balance, actually cause it to output a slightly higher concentration at altitude, just enough to keep the partial pressure of the agent delivered almost perfectly constant.
So the VBV's big trick is that it holds the delivered partial pressure steady no matter the elevation.
That's the take-home message. And that means the MAC value, the anesthetic depth you achieve with the 2% setting, is the same whether you're in Mumbai or in the mountains. No manual adjustment is needed.
That's a huge safety feature and a massive high yield point.
Okay.
Let's move on to the more external safety features of variable bypass vaporizers. What stops me from making a mistake as the operator?
The first line of defense is the agent-specific filling system. You can't just pour a bottle of liquid into the top.
You need a special key.
You need a key or an adapter that is physically unique to each agent. The vaporizer has a specific pin-indexed port, and the bottle adapter has a matching pattern.
So I literally cannot pour sevoflurane into an isoflurane vaporizer.
The key just won't fit. It makes it physically impossible to fill a vaporizer with the wrong agent, which would be a catastrophic error. These are the key filler or safety filler systems.
Okay, that's filling. What about when they're on the machine? The second major feature is the interlock mechanism.
Right. Most modern vaporizers mount on a special manifold bar, like a select-detect system. This bar has an interlock.
What do they do?
Two things. First, it ensures that you can only turn on one vaporizer at a time. When you turn one dial, it pushes out pins that physically lock the dials of the adjacent vaporizers in the off position,
Preventing you from delivering 2 agents at once.
which would be incredibly dangerous. And second, it ensures that when a vaporizer is on, the fresh gas flow is correctly diverted through it and not just flowing past it on the manifold.
And just the physical stability is a safety feature too, right? The locking systems and their positioning.
Absolutely. The mounting system locks them on tightly so they can't be accidentally knocked off. They are designed to be robust. However, that brings us to what happens when things go wrong.
Let's talk about errors and malfunctions, scenarios where the VBV output is dangerously wrong.
The most common errors revolve around the liquid level. Let's start with overfilling.
Putting too much liquid in.
Yes. If you overfill it, liquid anesthetic can get out of the vaporizing chamber and spill into the bypass chamber.
And if liquid gets into the bypass flow,
That flow is no longer clean gas. It's now carrying a huge, unmeasured, and uncontrollable amount of vapor. The result is a massive, acute overdose for the patient, a critical emergency.
what's the flip side? Underfilling.
If you let the vaporizer run too low, the wicks might become exposed and dry out.
So the surface area for vaporization plummets.
Right. The gas flowing through the vaporizing chamber no longer becomes fully saturated. The final concentration delivered to the patient will be much lower than what you have set on the dial.
Potentially leading to patient awareness during surgery.
A very real risk.
Okay, what about the most acute danger? Tipping of the vaporizer.
Tipping is so dangerous for the same reason as overfilling. It allows liquid agent to slosh out of the vaporizing chamber and get into the bypass mechanism or even the outlet port.
So again, you have the risk of a massive overdose.
Exactly. If a vaporizer is tipped more than about 45 degrees, it is considered contaminated. It has to be taken out of service immediately, purged with high flows of oxygen for at least 20 to 30 minutes, and ideally sent for servicing. You simply cannot trust it.
Let's quickly revisit the effect of high fresh gas flows. We said the VBV is compensated, but there must be a limit.
There is. If you use extremely high flows, say above 15 liters per minute, the transit time of the gas through the vaporizing chamber becomes very, very short.
Not enough time to get fully saturated.
Correct. The output concentration will start to drop below the dial setting because the gas simply can't pick up enough vapor in the short time it's in contact with the wicks.
And that limitation is really what stops us from using a VBV for a very, very volatile agent, isn't it?
It's one of the key reasons. If you had an agent that vaporized extremely easily, the amount of vapor it would produce would be enormous. You would need a tremendously high FGF to dilute it down.
Which would exceed the VBV's flow compensation limits.
And at the same time, that massive amount of vaporization would create so much cooling that it would completely overwhelm the bimetallic strip. The whole system would fail.
That sets us up perfectly for the comparison and exam table section. This is about summarizing the advantages and disadvantages of variable bypass vaporizer.
Okay. The main advantage is its mechanical reliability. No power required. It is robust. And as we've stressed, its automatic compensation for ambient pressure changes is a massive safety and convenience feature.
Constant partial pressure delivery.
That's the key phrase. They are also relatively easy to service and understand compared to more complex electronic systems.
And the main disadvantage.
The defining limitation is its inability to handle highly volatile agents. The design just can't cope with the extreme cooling effect and the massive dilution flows that would be required.
This leads directly to that absolute classic Viva question. Why can't Desflurane be used in a conventional variable bypass vaporizer? You have to be able to list the 3 physical reasons.
You must have this down cold. Number 1, high volatility. Desflurane's saturated vapor pressure is so high, nearly 1 atmosphere at room temperature, that the vapor is far too concentrated for a VBV's splitting ratio to handle.
Okay, number 1 is high volatility.
Number 2, overwhelming cooling. To get a clinical concentration, you'd need to vaporize so much liquid so quickly that it would cause a massive temperature drop, freezing the unit and making the output completely unstable. The bimetallic strip just can't cope.
And number 3.
The dilution problem. The sheer volume of vapor produced would require, and this is a good phrase to use, a tremendously high fresh gas flow to dilute it down to a safe percentage, far beyond what a VBV is designed for.
High volatility, overwhelming cooling, and the dilution problem. Got it.
Master those 3, it's a guaranteed question.
Now, let's talk about exams directly. Diagrams and exam presentation. When you're in that theory exam, drawing a good diagram is worth a lot of marks. What should we be prepared to draw?
2 diagrams are essential. First, a simple schematic of a flowmeter, Thorpe tube. Show the tapered tube, the float, and the needle valve at the bottom. Make sure you indicate where you would read the float.
And the second diagram.
A conceptual diagram of a variable bypass vaporizer. It doesn't need to be an engineering blueprint. Just show the inlet, the splitting valve controlled by the dial, the 2 paths for the bypass and vaporizing chambers, the wicks inside, and the outlet where they mix. And crucially, you must include and label the temperature compensation mechanism.
The bimetallic strip.
Yes. Show the bimetallic strip and indicate that it controls the splitting valve.
What are the key labeling points examiners expect on those diagrams? What makes them look for full marks?
For the Thorpe tube, label the variable annular orifice. And it's a great touch to note that the low flow section is viscosity dependent and the high flow section is density dependent.
And for the VBV?
The examiner wants to see that you understand the mechanism. So clearly label the splitting ratio valve and show how the bimetallic strip acts upon it to alter the flow based on temperature. That shows you understand the why, not just the what.
Excellent advice. Let's move into the final stretch. Viva traps and common mistakes. This is about high pressure preparation. What are the questions they love to ask?
We've covered them, but let's drill them again. First up, guaranteed. How does altitude affect the output of your variable bypass vaporizer?
And the answer is?
The VBV automatically compensates to maintain a constant delivered partial pressure. No manual adjustment is needed. That is the complete, safe, high-scoring answer.
What's the common mistake here? The misconception?
The trap is getting confused. Students either think all vaporizers need manual adjustment, or they can't explain why the VBV compensates. You must be confident in stating that compensation for pressure is an inherent feature of the VBV's design.
Next predictable question on safety. Describe the features in your machine that prevent delivery of a hypoxic gas mixture.
This is where you zoom out from just one component. You talk about the whole system, the proportioning link between the O2 and N2O valves, the mandatory sequencing of oxygen as the last gas downstream,
And your ultimate safety net.
and the independent in-circuit oxygen analyzer. You need to show an integrated safety consciousness.
And that final physics trap. List the 3 reasons why a highly volatile agent like Desflurane can't be used in a conventional vaporizer.
You just state the triad, instantly. High volatility, overwhelming cooling, and impractical dilution flow requirements. Practice saying it until it's second nature.
That's a fantastic pre-Viva drill. Okay, let's bring it all home. Summary and exam conclusion. Let's do a rapid-fire recap of the most critical facts.
All right, let's nail down 12 take-home points. 1. Flowmeters and vaporizers are a linked system, tested together for that reason.
2. The Thorpe tube is a variable orifice under constant pressure drop.
3. Low flow readings depend on viscosity. That's laminar flow, Reynolds number less than 2000.
4. High flow readings depend on density. That's turbulent flow, Reynolds number over 4000.
5. For safety, oxygen is always the last downstream flow meter.
6. The oxygen knob is unique by touch larger and knurled.
7. Back pressure from the circuit makes flow meters overread.
8. VBVs are temperature compensated by a bimetallic strip that adjusts the splitting ratio.
9. A VBV provides automatic pressure compensation, maintaining constant partial pressure at any altitude.
10. Key vaporizer safety features are agent-specific fillers and interlock mechanisms.
11. Tipping a vaporizer is an emergency. It can cause a critical overdose from liquid in the bypass.
And 12. The VBV can't handle highly volatile agents because of the extreme cooling and dilution problems. That is a rock-solid list. Now for the grand finale. For that 20-mark question, you need a powerful, structured conclusion to tie it all together.
Your model conclusion has to integrate the physics, the design, and the safety. You could say something like this. In conclusion, the precise and safe delivery of anesthetic agents is fundamentally dependent on the integrated function of flowmeters and variable bypass vaporizers.
The flowmeters, operating on principles of fluid dynamics and gas-specific calibration, ensure the correct mixture of fresh gases, with inbuilt safety features like downstream oxygen sequencing to critically guard against hypoxia.
The VBV then manages the complex thermodynamics of vaporization. It employs mechanical systems like the bimetallic strip for thermal stability and, most importantly, leverages its design for automatic pressure compensation.
Together, these sophisticated components ensure that regardless of environmental changes or clinical demands, the partial pressure of the anesthetic agent delivered to the patient remains constant and predictable, thereby guaranteeing a safe and effective anesthetic.
That's the kind of synthesis that demonstrates mastery.
That is precisely the level of understanding that will translate into success in these exams. You have the principles, you have the high-yield facts, and you have the Viva traps covered. Good luck with your final studies.
Remember, as you practice drawing those diagrams, don't just label the parts. Think about the physics. Why is that part there? What forces are acting on it? That's the depth that will set you apart.